Well, hi guys, it's Cliff here, a toolmaker from New Zealand. In this video I'm going to design and make a low profile edge clamps or two-part vise. I'll be going into the design and then machining it up. Well, in this video I'm going to design, develop and make two low profile edge clamps or a two-part vise. Be able to be used for both applications. So please follow me on this journey and I'll discuss different ways of designing and developing a product, and as I make it I'll throw in as many machining tips and tricks as I can. So the first thing to do before you do any of your own design is to study existing designs. Look online, look at all the products that are available, study all the manufactured products, all the developed products, look at all the YouTube videos of low profile and two-part vise builds. Follow them through. The more time you spend looking at other designs and critically analyzing them, the better. Gradually immerse yourself in the design and think about it over several days as your brain slowly aligns itself with the design process, and make sketches and ask questions. Why have this dovetail here? Isn't that going to have clearance and cause problems? Why have two cap screws? Is that better than one cap screw? Does it hold better on the table with two? Why is this one so high? What angle should they be? A shallow angle gives more force this way. A steep angle, look at all the different features. This style has a grub screw, but how much force can that grub screw apply and how long will it last? Make little notes and criticisms before you even begin, and then start sketching how you think a design would work that takes all of the good aspects of the current designs together in your design. You build it within the knowledge that you have, within the design constraints that you understand, with the end goal in mind. You start sketching it and rubbing out bits and redoing bits until you have a really good possible design. Now at this point, at this sketched, designed and prototyped in your head, you've thought about it, you've laid awake at night thinking about it, and you think this isn't going to work because that's going to rock over on an angle and that's going to come loose and this, that and the other thing, and slowly you erase that design and come at it from another angle. After a couple of days you're ready to start getting serious with the details of your design. And this is where the design process branches into two different roads. Either you have high-end CAD skills and you can solid model, CAD it into a solid model assembly and analyze it in its abstract sense on your computer. That's a really good way to do it. Or you're more traditional and you're better off, you don't have those high-end CAD skills, and you're better off to get a chunk of steel and start making it. And that has advantages too, because it allows you to test the prototype in various stages during its manufacture. I can do CAD modeling myself, but I don't have high-end assembly analysis CAD skills, and I'm just a basic CAD modeler. So I'm better off to use the traditional method and start making it from a block of steel and analyzing the design in its physical form as I go. I can do tests along the way and refine the design along the way. So please stay with me on this journey and I'll take you through the different stages of developing a design. So just two little blocks, and then felt pen mark the angles at 60 degrees and just bandsaw them. So I've just bandsawed those blocks out now, and I'm just looking at the design of the next stage. A lot of the designs, existing designs, have dovetail guides in this portion, or square guides, and I can't really see a good reason for having them other than it kind of looks cool and holds the parts together when they're off the mill. But when they're on the mill, really the way it works, there's no real need for those guides there. It just adds a lot of work and introduces probably as many errors as benefits. Makes it difficult to grind after they've been hardened. I don't know, I might be wrong. I just can't at the moment see why you'd need to do that. I need to mull that over for a while. Just thinking about this guided or not guided, if anything it's an advantage to have it not guided. This is it in its clamp position, but if you had an error in the parallelness of the setup, it automatically accommodates that error by the locking block floating up on an angle. And if it's constrained by a slideway and there's an error, you can see there you're only really getting point contact in the corner. It's not able to adjust its position. Here I'm going to machine the 30 or 60 degree bevels on the back of the blocks. Have you seen this type of inclinable tilting vise before? I made this just out of a basic little square-sided vise, and these side pivot plates are just screwed onto a base plate. They don't need to be doweled or high precision because of the fact that it's clamping up against the side of a square vise. It doesn't actually need doweling, it just perfectly aligns itself. There's a video on making this very simple little base plate called Incline Your Vise, I think. Go back a few years and you should find it there. Alright, well, time to do some testing. So I've tightened up the moving jaws, and as I discussed earlier, they've snugged and floated down to a nice parallel grip. I've checked it with shim underneath, and it's pulled down tight on the table, so the angle is pulling it down really tight. Now let's see, I'll put a dial indicator over here. Let's see how well it's holding. It's pretty well. I've got a long extension, so I've got a lot of leverage, but I'm getting a little bit of movement. So where's that movement coming from? I'm putting a dial indicator over here. Let's see whether or not those moving jaws are displacing under that movement impact, because what we're doing here is simulating a big cut, you know, a big face mill cut, for example. If it grabbed the work and tried to wrench it and move it, where's the weakness? Where's the first line of failure? So let's try tapping it here. And let's look up here and see if that's going to move. Oh yeah, see that? Okay, that tells us a lot. So what's happening is, what I thought was an advantage of the moving jaw being able to skew around on that face to accommodate a nice parallel grip, even grip, is now a disadvantage, because what's happening is that the whole thing is skidding. So the moving jaws are skidding on that flat face. And I hadn't thought of that. When I did the first trials, I saw it just as an advantage not to have that guided. But now I see it's a disadvantage. It's causing the jaws to skid on that surface. So they need to be keyed, not just guided, but keyed, because if they're just guided with little dovetails or little rebates, they're not going to be 100%. There's going to be a bit of clearance in there, and you know, any clearance in those guides will translate to skewing and movement, which will allow the part to shift by the amount of clearance. It needs to be something more like a quick change tool pose V key, so that it can slide but there's no clearance. So I need to think about how that could be designed. That would be a step up in the design of these wedge clamps. If that could be done, it would stop that little bit of movement, and any movement of a part is an error. So this is a really good example of product design via prototyping as you build. And you can learn a lot before the actual prototype is finished if you do it in stages. Obviously there's disadvantage in this method, because sometimes you have to hack the part around and it ends up by being a bit of a hacked up prototype. But the advantages are that you can do physical prototyping and testing and trialing as you go, and that's very difficult to do in the design stage by drawing or CAD modeling. And even solid modeling assemblies, you know, and there are not many of us that have got high-end CAD skills that allow us to solid model assemblies and have articulated moving assemblies that we can then analyze. But even those that do have those high-end skills that can CAD model solid assemblies still can't do these kind of tests. They can't put dial indicators on them and tighten them up and really trial them in the way that a physical model, a real prototype will allow. So I still think this old-fashioned method of designing by prototyping as you build has some real advantages. So the idea is, I'll put two little dowels to act as keys, 18 millimeters either side of center, and I'll offset them 1/4 of a millimeter so they stay in 1/2. So there I put in a ball nose cutter, a 1/4 inch ball nose cutter, and now I can drill and ream at 6 millimeters. So I'll drill through with a 5/8 drill and then ream with a 6 mil reamer. And now our 6 millimeter machine reamer We'll give it a fast feed rate so it follows the hole to the minimum diameter and doesn't try and act like a cutter and trepan out a bigger amount with any run out. And hopefully that's cut a nice tight size. Oh yeah, that's going to be good. That's quite a snug fit. Well, that looks good. So we've got it slightly more in one half than the other, but it should act like a key. I would encourage you, if you're doing a wide variety of work, to have a good stock of hardened and ground dowels. They're just so useful for different projects. They're not expensive. And you can have a range of metric and imperial sizes, fully through hardened or case hardened. They're not expensive and they're just so handy to have on hand. Okay, so we're all set up now with the improved design, complete with the guidance ridges or keys, those 6mm dowels, and we'll test it now to see how much more stable and well clamped it is. Okay, so we've tightened it up pretty tight. It already feels more snug than it did before. Bring the dial indicators into contact. Doesn't have to be zeroed, but alright, let's see what it's like. We'll smack it on the end. Oh yeah. That's a lot more secure. It's just locked in much tighter. So obviously what was going wrong was that these moving jaws were skewing around or skating around on that surface. And they really need to be guidance ridges to stop that. You know, just having a little dovetail in there with clearance is not enough. They need to be V-shaped guidance ridges, or semicircular in this case. You know, if you were just making one set for the home shop or for this prototype, the circular is okay, but a V-shaped guidance ridges would be even better. When I say V-shape, this is the type of design I mean, like on a quick change tool post. So you get a big flat there, a V-shaped flat, giving it really positive guidance. So there's no clearance as it tightens up. The trouble with a non-V shape, just a square or a dovetail, is that there has to be clearance and spring and flex, and so the whole thing can move a couple of thou, and a couple of thou movement means it's unstable because the whole thing can shift slightly, whereas when it's V-shaped, the more you tighten it, the less clearance there is. So having been through the process of designing and developing these edge clamps, you become more and more attuned to the various design features and aspects of V-clamping, and the more I look at the different designs online, I can see a whole lot of badly designed edge clamps, ones that have serious flaws in them, and these are manufactured products that are being mass produced. You know, copies of original designs, mass-produced in China. You can buy them for a low price, but they have serious flaws in the design. Some are worse than others. Clearly, they either were not originally tested and the design refined, or they were tested, but the product was manufactured knowing there was a flaw in the design. I don't know whether it's innocent or cynical, but manufacturing has gone ahead anyway. And that's the case for a lot of engineering products. They're just not well developed. There's lots of ways they can be improved just with a little bit of effort. And so we sort of innocently buy products that we assume have been well designed, but they really haven't. Well, enough talking, let's give it a try. So I've got a couple of fairly blunt inserts in there, 2 and not 4. Put on a fairly deep cut, 0.5 millimeter deep. I'll set the feed rate on the fastest feed rate I can. I haven't hardened the jaws yet or put serrated edges on the front, but let's just see how stable it is in this situation. Well, that's fantastic. I think I can justify further development now. I think it would benefit from serrations on the front of the moving jaws that bite into the work, and then hardening them so that they're really durable. Alright, well, they're made from O1 steel and oil hardening tool steel, and we've heated it up to 820 degrees and soaked it there for a while, and we're going to biff it into canola oil and quench it and see if it goes hard. This is a really easy steel to heat treat, O1 steel. I'll let the oven cool down now to about 250 degrees C, and then put the parts back in for tempering. At about 250 degrees C, it should temper them back to about late 50s Rockwell C, which is still pretty hard, but a lot more durable. Okay, well that's them hardened now with those teeth that should bite in well and be durable. I just put a bit of fine lapping paste on the surfaces just to lap them together. It's not ideal. Ideally they should be match ground, but you know, it's good enough for a prototype or for a one-off build for a home shop situation. So this would be a version 2. I've just stretched some of the dimensions to be a bit more optimal. If you're interested in making something like this, just pause your screen and take a print off. Take a screenshot and take a print off. Most of the key dimensions are there. The rest of them you can work out for yourself. Nothing too critical there. Well, they work really well and they should do the job that I need. I think the version 2 would be proportioned better. But the perfectionist in me wants to build another prototype to a different design and see whether a version 3 would be better still. But I'm not sure I can justify the time developing a product that I would probably never manufacture. So I might never get around to building a version 3, but I can see ways of improving it further by rejigging some of the design features. And finally, if you're new to my channel Thread Express, are you aware of Thread Express, a thread milling and indexing attachment that fits on your milling machine, and you can index and cut threads of any pitch within its range. This is available for download as plans and drawings from my website, Hallmark Design. I'll put a link in the description below. You'll find it on my channel. Have a look at recent videos on this attachment. Thanks for watching this video. Hopefully you learned something along the way, something was useful to you. Please like and subscribe if that's the case. Stay tuned for the next video.